Welcome everybody to Breaking Boundaries with Pellet 3D Printing. My name is Madeline Pryor and I am the moderator for this webinar. I will be joined by Frank Clemens, Toni Iborra and Zoltan Mayas. Good morning, good afternoon, gentlemen.
Good afternoon.
Good afternoon.
I will introduce the panelists in a little bit, but as people are still trickling in, I just wanted to take the moment to go through an introduction and introduce you to the webinar. Also, just so you know, this webinar will be recorded. It will be available afterwards on YouTube through 3D Native's YouTube channel. If you would like to be notified when it is up, you can subscribe. And let's move to the next slide now, please. Great. So as you can see here, we have the agenda for the next hour or so. After this introduction, we will be moving into an explanation about what pellet 3D printing is, as well as a profile of Tukmaker, who is one of the leading manufacturers of pellet 3D printers in the industry. Next, we will take a closer look at some of the benefits of pellet 3D printing, as well as the sectors in which it can be used and some of the applications, before finally turning to some user cases from the EMPA, which is the Swiss Federal Laboratories for Material Science and Technology. At the end, we will actually have a Q&A, and I would like to take this opportunity to ask you all, if you have any questions, please do ask them in the Q&A section. It is at the bottom of your screen. I will keep an eye on it, and we'll have the last 15 minutes to ask the panelists some of your questions. And let's turn to the next slide, please. So here we have the panelists. First, I would like to introduce you to Mr. Zoltan Mayas, who is an international expansion project manager at Tukmaker. He has more than 20 years of frontline B2B business experience in international sales and marketing, and has studied management, sales and marketing at a university level, and he also holds a degree in digital and social media marketing, as well as a master's degree in international business and life coaching. He has created several successful international sales campaigns, developed strategies, and led sales teams. Additionally, he has managed industrialization and sales expansion projects and opened new markets in several countries. Since 2021, he has been in charge of the internationalization of the Tukmaker brand as a country manager. Also from Tukmaker, we'll be joined by Dr. Toni Iborra, who is a project manager and materials specialist, who graduated from the University of Valencia with a degree in chemistry, with stays at the University of Manchester in the UK and Pontifical Catholic University of Argentina. He began his research career at the University of Southampton, where he obtained his PhD in chemistry for his research based on materials with photocatalytic properties, and where he also carried out teaching activities. He has presented his work at national and international congresses, including at the University of Oxford and EMRS Strasbourg, as well as published peer-reviewed articles in first quartile scientific journals. He is a lecturer at the Francisco de Vitoria University and professor in chemistry at Florida State University, teaching chemistry 1 and 2, as well as experimental lab. Since 2021, he has led the commercial strategy and positioning of the Nova Spider project at IT3D Group as an expert in the field of material sciences. And last but not least, Dr. Frank Clemens is a group leader in the Laboratory for High Performance Ceramics at EMPA, the Swiss Federal Laboratories for Material Science and Technology, Switzerland. His scientific and applied research belongs to thermoplastic processing of powder-based sensors and structural materials. His group focuses on national and international projects in this field. He works with physics, chemists, material scientists, and engineers together to investigate activation energies on different processing steps. Besides this, he develops new strategies for the processing of functional ceramics and soft sensor materials and structures. And since 2003, he has been a lecturer at ETH Zurich, and between 2010 and 2021, a lecturer at ZHAW. He has more than 150 peer-reviewed articles and patents, so I think it's safe to say, between our panelists, we are in safe hands to explore this topic. And let's move to the next slide to get into the thick of things. So additive manufacturing at a glance. I expect that many of you here are already familiar with both additive manufacturing But I just wanted to take an opportunity to take a closer look at the processes that are used. For those of you who don't know, on the graph on the screen, you can see the many different processes that are used in additive manufacturing. But by far, one of the most popular are extrusion methods, though called FDM and FFF here. There are others that hold the extrusion name, and in this graph from Sculpture, they showed that the vast majority of companies who are adopting additive manufacturing are adopting it through these extrusion rather than other methods for a number of reasons, including cost and ease of use. Next slide, please. However, another trend that is very clearly happening in the AM market is that it's moving quickly into industrialization. Though this has been a factor since the beginning of AM, over the past years, we've seen it becoming more and more of a factor. In fact, in this study from Markets to Markets, though in 2020, the industrial 3D printing market was valued at 2.0 billion US dollars, it is expected to increase to 5.3. That being said, when you think of it, these industrial projects, often extrusion isn't what comes to mind. Instead, it is other processes. This is where a technology like pellet 3D printing comes in. Thanks to pellet 3D printing, users would be able to use a wider variety of industrial printing materials at a cheaper cost and faster than with many other methods. This could really help to push industrialization in the AM sector, allowing it to become even more securely a method for manufacturing through a variety of fields. Next slide, please. And now I will leave you in the capable hands of our panelists. Again, do not forget to ask questions in the Q&A section, which we will have at the end. Thank you, gentlemen. You can take it away.
Madeleine, thank you very much for the fantastic introduction. I also would like to welcome everybody. You know, I would just cut right in the middle of what we're going to talk about today. I'm looking forward to a nice hour spending together talking about pellet printing. So, as we saw on your introduction slides, the most popular manufacturing technology is extrusion. So, what is pellet printing? Well, it's not very difficult to explain. Pellet printing is when we're printing using pellets. We can call it FGM, fused granulate modeling, or direct extrusion printing. Something that I wanted to say, that every filament starts as a pellet, as filament manufacturers using pellets to make filament. So in essence, printing with pellets is jumping one step in the material chain. Printing using industrial pellets or almost any type of plastic waste converted to pellets, it allows that possibility that no other technology did before. There are various advantages there. We will talk about material options. Toni is going to go into materials. So that's one of the main aspects when it comes to pellet printing, and obviously lower cost. But there are many others which I will touch on, but I think you will also draw your own conclusions towards the end of the webinar. So we could move to the next slide, please. So what do you need for pellet printing? You need a pellet extruder. As you can see here, these are the Tukmaker pellet extruders that we are using in our printers. In essence, these are similar to traditional extruders, except you have a hopper, which you could see there marked with number 1, the white hopper on the top of the extruder where pellet goes in there. Also, we are just launching an auto feeder that will feed pellets directly into the extruder. Frank will be talking a lot more about extruders, so I would just leave it at that point. A couple of things with Tukmaker, the extruders we are fitting to our printers, they go up to 300, 350, optionally to 450 Celsius, giving additional possibilities with materials of higher melting points. And obviously these are developed by us and these are specific extruders for pellet printing. So we could move on to the next slide, Frank, if you can. Yeah, here just basically put in a picture so you see a pellet extruder in action. Like I mentioned before, there's a pellet hopper on the top of the extruder fitted to the 3D printer. We can move forward. Another picture, filling manually the pellets into the extruder while the machine is printing. So, as I promised, a bit more reasons, part of cost and materials using pellet printing, and those were the reasons why Tukmaker decided to start focusing on pellet printing. One of the most important one, or the first one that comes into mind, is the freedom of choice of material. You could use a wide array of materials there, as I mentioned before, up to 350 degrees. The second would be limitations in the development of new materials. We work with a lot of customers who want to test and try out new materials. Pellet technology makes that a lot more easy, a lot more convenient, and eliminates the need of creating filament from those materials. I also listed there advanced technical materials, custom composites, and adding dyes, additive fibers. I leave all that to Toni. He knows a lot more than me about this. So we'll see a lot more information in the material section of the webinar. The fourth, materials in the filament process, yes, they can lose or transform part of their properties. That also can be avoided if you directly use the pellet. Certification on materials, as Toni will mention as well, it allows to work with approved materials for different industries, which is being a challenge for many. The sixth is speed. It's often forgotten and overlooked, but pellet printing can increase the speed of printing by using different nozzles. Frank will get into the details of that as well, of how much and how speed can be increased by putting out more material during the printing process. The seventh was environmental benefits, as pellet printing makes easier to use recycled or remanufactured recycled material. It's simply more practical. As you might see, the title says 8 reasons. I have 7, so the 8th went to the next slide because it's slightly important for many. The cost of printing obviously depends on the material you're using, but estimated is 60 to 90% savings on printing cost per kilo, depending on the type of the material you use. Here's a quick comparison. The source from 3DX Tech, comparing PETG and Ultem Pellets pricing. I think it's not there's no rocket science. Pellet is lower cost material because we're skipping one step in the process of preparing material to be printed with. Next slide, please. So at this point, some of you might be asking the question, who's Tukmaker? So I just wanted to give a couple of quick facts about the company. We're building performance-focused industrial-grade 3D printers since 2014, always focusing on the prosumer industrial-grade machines. We have in-house manufacturing capabilities in the north of Spain. We tailor-make size and custom extruder combinations. So we work on projects with companies in terms of specific size, specific number of extruders, up to 4, and I will discuss a bit more about the different head combinations that are available. We are the first to the market with the pellet printing technology, bringing it to the desktop aimed to prosumers, and we work with partner training programs and working with specific solutions for customer needs. So next one, please. The available models, we have the NX, which is the smaller one with a printing volume of 2918-200. That was the first smallest machine we fitted with pellet extruders. We can move to the next one. Our best-selling range, the Bigfoot range. These are basically different in size, 200, 350, and 500 in terms of height. The mechanics and the build is the same. They are all built with pellet heads. They can be IDEX, independent dual extruder systems. As I mentioned before, we can do custom sizes and custom number of extruder heads fitted on the Bigfoot Pro series. Next one, please. And the possible combinations, which is, I believe, unique in the sector. We can combine different extrusion technologies in the same machine between Bowden, direct drive, and pellets. So you can potentially choose a dual extruder that both of them is pellet, or you could do direct drive and pellet, which is quite popular, using two different materials, one for support material, one for building materials. But as you see, combining these three extrusion technologies, 6 possible mix and match is available at in our Bigfoot range. So this I think sets the tone for the rest of the panelists on the webinar. I think this will, they will go into more depth in terms of materials and technology. So I would leave the screen for my colleagues Toni and Frank. Thank you very much.
Thank you very much, Zoltan, for your presentation. Also, thank you, Madeline, for your great presentation. Well, my name is Toni Iborra. I'm a material scientist at Tukmaker, and today we're going to talk about pellet technology. Can we go next, please? Slide. So why pellet technology? Well, traditionally 3D printing has made use of filamented materials. So the problem is that the currently 3D printing is limited to those materials that exist as filaments. So this is a handicap when it comes to the evolution and the expansion of the 3D printers. So in this context, at Tukmaker, we decided to go to the origin. We decided to go to pellets, which are, as you all know, the raw materials from which all filaments are manufactured. So why pellets? Well, many times the amount of material that we need for filament 3D printed is minimal. So this is one of the reasons why many polymers that are used in the industry are not filamented, due to the high cost that it will entail. So, however, thanks to the pellet technology, we can work with a wide range of materials in the pellet form. We can move. Thank you, Frank. And among these pellets, we can highlight certified and also FDA-approved materials for, that for some fields, such as tissue engineering or the biomedical sectors, the use of FDA-approved chemical grade, biocompatible materials is required, and currently they are only available as pellet. There is another advantage that we can highlight, and this one is a high flow and deposition rate. So the pellet feedstock allows for much higher deposition rates, and well, consequently, we can print bigger volumes, bigger parts. However, as the build rate increases, the ability to achieve the desired geometry and in some cases the surface resolution can decrease. At Tukmaker, we work typically for pellet extrusion from 0.4 millimeters to 5 millimeters in range of diameters of those nozzles. So with large deposition nozzles, large amounts of materials can be extruded, allowing for more material output from the extruder and therefore increasing the build rate. Another advantage that we can highlight, probably is the main one, is lower printing costs. So, well, both filaments and pellets, the 3D printing thermoplastics start out as pellets. So filamented materials are made by heating pellets, as my colleague Zoltan said, and forming them into filament. So using the pellet technology, we are skipping this process. So we have one less heating cycle, which potentially means that the pellet thermoplastic will process easier, they will perform better, and cost less comparable with filament. Here in this slide, for example, we can have a comparison between I think this was PLA pellet and PLA filament. Another one is bigger prints. So because of this lower throughput and the high resolution on filament printing tends to be used more for smaller parts. I mean, is it true that bigger parts also are possible using filament 3 printing, but it might not be economical or efficient? On the other side, on pellet printing tends to be used for larger parts, bigger volumes that can benefit from its faster throughput. Additionally, during filament 3 printing, we always have to make this technical step of changing the coil. So this is something that we can avoid using the pellet extrusion because we have an automatic feeder that is automatically feeding the pellet extruder. Another one is that we can have multi-material 3 printers. So we can combine up to 4 different independent heads. We can combine pellet extruders also with the incorporation of both and or direct drive heads. We allow for the combination of pellet extrusion with filament extrusion. In the next video, we are going to be able to see one of our devices, one of our machines working, okay? So this one contains 4 extruders, 2 of them are pellet and 2 of them are filament. So the first one is going to print the outer part of that structure using filament 3 printing. Then that same structure is going to be filled using a pellet extruder using a different polymer at different temperature. Then again, the same head is going to print a second structure, the outer part, and another pellet extruder is going to deposit a different material compared to the other one. And finally, a third structure. Now it's going to be printed, the outer part always with the same blue material, the blue polymer, and then it's going to be filled with another filament. So we have 4 different materials, we have 4 different extruders and 4 different temperatures. So which sectors we can, so thank you, Frank. So which sectors can benefit from this pellet technology? So we have biomedical sector, tissue engineering, drug delivery, and energy storage. We also have certified sectors. Can go one more, please. Thank you. And as well as railway, mechanical engineering, prototyping, and automotive and aerospace. So yeah, as previously mentioned, for the biomedical sector, chemical grade FDA-approved polymers such as polycaprolactone or polylactic acid are required. So this can be used to fabricate the scaffolds using different blends that contain active biomolecules such as antibiotics in order to treat different pathologies or infections. And here we can see some biomedical applications just to give you another example. Blends containing PLA and an inorganic material. In this case, in this slide, we can see that they are using calcium phosphate, has been widely studied for bone regeneration. Also for the mechanical and engineering field, and also prototyping, the validated pellets include many performance match grades to provide application-specific property profiles. For example, Valox pellets, PVT plus polycarbonate, combine heat and chemical resistance, and as well as outstanding electrical properties. Other fields that can benefit from the pellet technology include prosthetics. So which can be made using polymers that they are functionalized and they can have antimicrobial properties such as silver or copper nanoparticles. Then we can see now flexible. If we go one more, please, Frank. Yeah, we can, well, I will let Dr. Clemens from EMPA to go in details on flexible materials, but our pellet technology has shown to be able to print thermoplastic elastomers with a short hardness of 18.8, which is something that is currently not possible using direct drive filament 3D printing. Moreover, we can use additives to synthesize composite materials. So the customer or the researcher can fabricate their own custom material blends by combining different pellets. You can easily add dyes, additives, or reinforcement fibers to the mix to create custom-made composites. And if we go another slide, also another sector which is quite interesting, and also I'm pretty sure that Dr. Clemens is going to be able to go in details, is that we can use pellets loaded with a relatively high percentage of ceramic materials or metals. This can be extruded to obtain ceramic and metallic structures after post-processing. which basically consists in removing the organic matrix and annealing, which leads to the corresponding ceramic oxide or metal. So yeah, so basically that will be all the advantages of the pellet printing on some applications. So thank you very much for joining us.
So thank you very much, Toni. Thank you very much, all of you, for having the opportunity to show a little bit the work what we are doing at EMPA. And I would like to demonstrate you today how using screw extruders for research and development of things where the filament extruder has some problems and some limitations. So before I will start with my presentation, I shortly would highlight where I'm coming from. So as it was already mentioned, I'm coming from EMPA. EMPA is an institute according to the ETH domain in Switzerland, and we are located at 3 different places. So shortly, just a second. So on one hand, we are here in St. Gallen, in Dübendorf, and in Thun, and our mission is that we would like to do research and development for material and technologies for a sustainable future. And we typically, EMPA is collaborating with national, international laboratories, industry, universities, and government and society. So as it was already mentioned, I'm coming from the Laboratory for High Performance Ceramics. And at this lab, we are focusing on powder synthesis, advanced shaping technology, where also the additive manufacturing and the fused deposition modeling, fused filament fabrication, or extrusion, material extrusion-based additive manufacturing belongs to. And then we also focus on functional ceramics and composites. And my group is split in 2 parts. So on one hand, my group is developing soft sensors based on an elastomer, where we include some inorganic fillers, which gives then the functionality inside the elastomeric matrix. And the second part is that we are working on ceramic sensors, which, for example, we can use then for structural health monitoring, self-regulating heaters, or transducers. So let me now start about the screw extruder for material extrusion additive manufacturing and where we see the advantages. So first of all, if we go for material extrusion additive manufacturing, as it's called nowadays, some people of you knows it also by the word fused deposition modeling or fused filament fabrication. We can typically work with 4 types of different extruder heads. So one extruder head is based on an air pressure or a syringe, where we can press a paste through a nozzle, and then we will build up layer by layer and build up our 3D model with it, or a 3D objective with it. The other possibility, if I have not a paste anymore, if I go more to thermoplastics, then what I can do is I can use a so-called Bowden extruder, and this Bowden extruder will typically have the gears at a different place where the printing head is. By that you can make the printing head lighter and you can print faster and it's more precise. However, the filament has to go through a polymer tube before going inside the printing head, and this can be sometimes a problem if you work with so very soft materials. Another possibility is then the direct drive printing head, where the wheels or these gears are directly at the printing head, and then these gears will push the material inside the hot end of the printer head. Last but not least, and this is what we are talking about today, are the so-called screw extruders or pellet extruders. There are several names for the same technology. So typically we have here a hopper, and the pellets are pushed inside the screw extruder, or inside the extruder by the screw. So the screw is pushing the pellets inside the extruder head, and there the pellets will be then compressed and melted, and then we heat up with in this hot end. You have then the melted polymer, and this will be then extruded again through the nozzle. So very often the question is then, which technology is the right technology to use the different materials? And here is a little bit an overview about the 4 different printing heads, and you see the main advantages for the pellet extruder is when you want to work with high printing speeds, and it was already mentioned. And then also when we talk about material abrasion, and when you have materials which has a very low stiffness. So for example, elastomers. Attention, when I'm talking here about material abrasion, this means that when you have a very brittle filament, that these gears which you have, they normally rupture your filament, and this is called then by material abrasion. So the abrasion on the filament is meant here. So here you see a view of a screw extruder where you see here the hopper, the screw here, which brings the material through the nozzle where then the material goes through. And the idea what the people had when they were developing this kind of systems was that they wanted to mimic a little bit the things which has been already explored for these multi-component injection molding processes, where you, for example, can print toothbrushes where you have soft parts and rigid parts already together. And typically those systems or those devices, they are printed in one shot. And so you can combine soft and brittle materials. It was already mentioned that you have other advantages. And what I would like now to show a little bit is, so what will be, or let me show you 2 cases where we see that the screw extruder has really a potential, a high potential, and really can, we can use it to further develop new structures and new parts by using this kind of technology. So the first part I would like to look on is soft materials. So when we look on soft materials, as the name says, these materials are soft and they have a high flexibility. Unfortunately, they also have a high Poisson ratio, which is close to 0.5. And that means when I push from the top, then typically the material is bumping. And by this, for example, it will block directly inside the Bowden extruder. Another problem is when you work with a direct drive and you push from the top, you have this kind of buckling here. So that means the stiffness is not enough so that you can really bring or transfer the load from the filament which you need. So it will work like a piston in a piston extrusion to push the material through the hot end. And these are the main reasons why here filament printers have a huge limitation, and that's the reason why the direct drive can achieve or can take over these materials. However, we have to say that still now the resolution for printing head, the screw extruder, has a little bit lower resolution at the moment what we have, but nevertheless we can really print materials which are not able to print with this kind of materials with a direct drive. On the other hand, let me look on the brittle materials, so ceramic or metal filaments. And here typically we have a low polymer content, we have high filler content logically, so because we want to decompose afterwards the polymer, and we will then use a sinter process to consolidate the material and to have a dense ceramic or metal part. Therefore, what we need is, for the printing part, we need a good fusing of the small polymer amount which we have inside. On the other hand, we need a very good decomposition of the polymer so that we can remove the polymer before we do the sintering process. And very often the consumer wants to use a feedstock. A feedstock is a material which belongs on ceramic or metal powder and a polymeric binder. And this has been already used quite a lot for powder injection molding. And so it would be great if we can use powder injection molding feedstocks also for 3D printing. With a direct printing head, this is clear that it cannot be used. Bowden extruder, also clear, and also with a direct drive extruder, the problem is that these materials are typically so brittle that they will fracture or have high abrasion at the area where we have the gears. So these are two material classes where screw extruder printing head makes sense from our perspective, and where we already use these materials. And here you can see now a little bit some work which we already did in the last years. So this is, for example, a pellet extruder which we have here. And with this pellet extruder, we printed some discs, first of all. And you see here the bottom layer, which is quite smooth. The top layer is a little bit more roughy. But we used here 4 different binder systems, and we made a ceramic feedstock out of it. And you can see that 2 of them, they were able to print. The other 2, there is 2 max waxes inside. So that means when we start to print with these print heads, then we have a phase separation and the waxes are separated from the feedstock. However, interesting for these 2 feedstocks which we made by ourselves with a commercial binder injection molding binder system. So you can see here that you have a nice linear relationship between the feeding rate and the extrusion output. However, one thing has to be mentioned, that when we go for high speed, we lose a little bit the densification with this kind of printers. So this is something where we still have to investigate furthermore, so that we can, even when we go with high speed, we can keep a very dense structure, as you can see here, because this is clearly needed when you want to have a good mechanical properties for metals or ceramic parts. One thing you can also see here is when you use not the right binder system, then you can also have here delamination. So you really have to test if your feedstock can really be used for 3D printing or not. Another part which we see at the moment when we compare, for example, with filaments, with cold isostatic pressed materials, you see that when we go for 3D printing with a screw extruder, we have a lower density, but this is also something where I think this belongs more to the binder system and not to the printing device itself. So here it's clear that even when you work with a injection molding feedstock, you have to be aware that you probably will not get exactly the same performance as you would expect from your injection molding process. We also work with this kind of pre-ceramic polymers, and also here we need to use the screw extruder, because the material gets very brittle, even though that the pre-ceramic polymer is a thermoplastic material, but the viscosity is much too low to use it to produce very nice and flexible filaments. And you can see here different results which we achieved. So you see here different binder compositions, and for example, in the solvent debinding process, you can see that we can remove a part of the binder already, but after the partial debinding, you see with one binder system, we still have here some parts inside the samples which we printed, which are not fully debinded. And when you sinter them now, you see then here also some cracks here inside, which means you lose the mechanical properties. So also here the point is that the screw extruder, from my point of view, is a very good alternative to a filament printer, but the binder system has to be still or further investigated so that you get nice parts out of it without any kind of defects after sintering. So here you can already see some ceramic parts which have been printed successfully for different applications. So you see some small parts, you see some parts for watch industry, you see some implants which were printed. You can see here that they were printed with a support material, and you can also see here that you can also print very large structures based on this additive manufacturing technology. So the second part which I wanted to show you are the work which we did in the part of soft robotics, mainly grippers for soft robotics. And when you work with these soft grippers, which you can see here nicely in the video, so this is by applying a pressure, an air pressure, and then you can, by the air pressure, you can deform this device here. And the interesting part is here that for this device, which you see here in the video, you have to print about 3 hours. To make these things, what you see on the left-hand video, you need almost 2 to 3 days to do the whole casting process to get this kind of soft grippers. So therefore, you see that the advantage is here really that you can lower the time to produce those structures, and therefore you can make much more design experiments and see which is the right design for your application, for example. And we published this already last year in Extruders, so where we also introduced or included a sensor inside, which is another part. That means by these multi or these 4 printing heads, which are available nowadays, you can already integrate some sensor materials inside. And that means you can go even one step ahead, and you can print on the soft materials, chemoresistive, thermoresistive, or mechanoresistive materials, and you can investigate the deformation of the structure, or you can investigate the temperature of the structure. So is the system heating up? So is it too close to a heating area? Or you can even detect chemical species. And this is what I would like to show you here inside these 3 videos. So you see here one example for this pneumatic actuator, where you see that resistance changed by changing the deformation angle, which you can measure then with this special piezoresistive strain sensor on top of it. The other possibility is that you can measure, for example, here the solvent. So that means you measure here the vapor of the solvent, which is above the liquid. And you see when we bend it and when we extend it, then we bend it and extend it, you see that then the current always goes down because the concentration above this liquid increases over the time. But you can really nicely see that when we always go close to the surface of the liquid, we always have a huge decrease of the current, which means we can detect nicely the chemical species inside. And the last video, which you can see here, are these kind of soft grippers here for fruit. And you can see that by these strain sensors, which are printed here on the side of these grippers here, you can see that you can detect different sizes. So that means when you have, for example, different fruits, you can really select them and place them at, or put them at different places. So these are the applications which you can do with this kind of new technology which is now available. And so let me conclude my part with it. So I wanted to show you that you should now use not anymore the word FDM and FFF. You should talk about material extrusion additive manufacturing. And there is also the screw extruder printing heads, which belongs to this additive manufacturing platform. And the interesting part with the screw extruder printing heads is that you can print materials that are not able to print with other kind of printing heads. And one example I tried to explain you is the commercial ceramic injection molding feedstocks, which you can nicely print with this kind of screw extruders. However, take into account you cannot use all kind of ceramic injection molding feedstocks or metal injection molding feedstocks. So you have to look a little bit what is their composition, because fusing you need anyhow during the printing process. Yeah, and therefore waxes might be a little bit a problem as far as we see at the moment. So another part which I showed you are the soft materials, and this is really a big challenge which I see, because I have not seen so much printers which are able to print a shore hardness below 10A, and I only can see that these can be done by these kind of screw extruder printing heads, where we have the possibility to even go lower. We were already able to print shore hardness of 5, but this is a different story, and I think it's a little bit overloading for today. Finally, the nice thing is that we have now also the possibility that we have a dual or 4-head multi-printing. So that means we can integrate, so we can print soft materials, we can integrate sensors, plus we have the possibility that we can also print support material, and therefore we can really make very complex structures for soft robotic, medical, or implants, or prosthesis, or any kind of other applications which are a little bit more complex than this. Finally, I would like to thank my team for providing me with all this work which I showed you today, and for sure all the funding support which I get from the different agencies. And I would like to thank you for your attention.
And with that, thank you so much, Jonathan, for the interesting presentation. And we can turn to some questions from our audience. We actually have quite a few questions already. Please do not raise your hands. If you have a question, you can write it in the Q&A section. I will be choosing based on number of votes. You can upvote questions you would like answered, and otherwise in the order in which I see them. So I suppose I can ask the first question, which is, do pellets require any pre-processing before printing?
Well, I can go first, and I don't know if Fran wants to add something, but it will depend on the kind of the material. There are some materials that they require to have well, you need to remove the humidity. So it will depend on the material. That's the main question.
Okay. And another question is, with pellet extrusion, how can you prevent clogging?
Good question. It will depend also on the material. So you are going to have some materials that they are going to show more clogging than other ones.
Okay, thank you. A question that has just increased in popularity is, could you please tell us the price range for the Tukmaker printers?
Zoltan, that's your turn.
I guess it's my turn then. Look, it depends. Like I said, there are different sizes, different combinations. If we talk about 2 heads, 4 heads, a single extruder, the Bigfoot range with 3 different sizes, the NX, it really depends. I suggest to look at everything case by case. I'm not sure if you're sharing our contact details, but I'm happy to attend any specific request, and we're happy to quote solutions.
Okay, great, thank you. The next question we have is whether it would be possible to directly mix or blend polymers within the extruder of the printer.
Within the extruder?
Oh, therefore the length of the extruder is too short. Excuse me.
No, no, good. That was awesome.
And we need to have another screw inside. So I think this is something where I see a big future for these pellet-based extruders or for the screw-based extruders, because this technology is well known. Yeah. So if you go in polymer technologies, I mean, how can you process thermoplastic polymers without an extruder? So therefore, this technology is quite old, and I think people will come up and find solutions, probably also to solve this problem.
Well, I guess we'll have to see what's coming. Additive manufacturing certainly moves fast. For the next question, I think this might be towards you, Frank. For the ceramic pellet materials, how high of a particle loading can you print, and what is the ideal particle size, and what is the particle size range?
So what we already did is we printed with, I always call it submicron powder. So this is a powder which has a particle size in a range of 0.5 to 0.8 micrometers. If you use something like this, then you typically have a little bit of lower powder loading than with ceramic feedstocks, so injection molding feedstocks. So that means we started with printing of 45 volume%. However, we could go up to 49, 48 volume%, but then abrasion is the main problem, because take into account these pellet printers have been made for polymers, not for ceramics and metals, and therefore the screw nor the barrel has been hardened. And therefore I would always advise to go a little bit lower with the filler content.
Okay, thank you very much. I'm actually going to jump a little bit because just a reminder to everyone, do try and put it in the Q&A section, but I did just happen to notice that there was a question in the chat, which is, what are the mechanical properties that are achieved post-printing with the pellets?
Is this for me or for?
For anyone who would like to answer.
I think they are talking about the mechanical properties of the ceramic materials, ceramic metallic materials.
So for the ceramic metallic, I can tell you, so we did now a study which we will publish this month, and there we were testing. So this is what I showed you, the cold isostatic pressed samples with filament printed samples and with samples with a pellet printer head, and there what we found out was that the properties between a filament printer and a cold isostatic pressed sample are quite similar. So statistically, we cannot see a big difference. For the pellet head printer, we only have 50% of the strength at the moment. But this is something where we believe, probably you saw this before, maybe I can go back to my slide here, then I can quickly answer this here. So I hope you can see the slide here. So you see here, you still see here the different layers after thermal debinding process. And we believe that this is at the moment a problem. So the fusing of the polymers is the problem and not the process. But this we have to further prove on. But when I look on the things what we have been achieved by the by this elastomers here, by the thermoplastic elastomers, take into account we apply here 500 bar. And this is already quite high to deform this part. And even that means that the material will not blow away or something like this. So stability is quite good.
Great, thank you very much. Next question that just gained in popularity for anyone who would like to answer is it possible to print PEEK using pellets?
Okay, so with our printers, it is true that we have started to use PEEK. However, only it is limited to a small part. Okay, so we are not able to print PEEK at bigger volumes, because we will require chamber temperature conditions within the chamber. So we have worked with big for small parts for a tensile too, but we are not getting the results for big parts.
Makes sense. It's a challenging material overall in extrusion and other methods as well.
We are working on it though.
Well, we'll wait to see, shall we?
Yeah.
A next question, I think, for Toni, actually, would be, in biomedical applications, what material would you say is the most used, and would it be approved? I'm assuming that is FDA approval?
Yeah, I will say PCL. PCL and PLA, both are quite used, FDA approved materials. They are biocompatible, they are biodegradable.
Makes sense. And then another question is, does the printer by Tukmaker allow mixing master batches or the incorporation of plastic waste?
Yes, this is something that, well, it depends on the form of that plastic waste. So we will need to go into details again, and we will need to see the diameter of those particles. But we have clients that they have explored this part, and we consider at Tukmaker that this is something interesting.
And another Tukmaker question is, what is the difference between the Tukmaker pellet extruder and other pellet extruders that could be found on the internet?
Okay, I will say that the main goal here is that our pellet extruders, the printer is desktop made. So first one is also the size. Okay, so I don't know if Franklin wants to add something that he has shown compared to other 3D printers that he might use.
I don't know what I should say now here. Huh? Well, yes, there are other printers. The price range is completely different. I mean, this is so the prices for those kind of printers, which, so when I started with Tukmakers, I think 4 years ago now, so where the first pellet printers came on the market, then we were looking on a few different kind of printers, and typically the prices were between 50,000 and 100,000. There was some which were a little bit under development state, which were a little bit cheaper. But therefore I have to say the pellet printers were cheaper, and that's the reason why we started with this, because they were in the range of a 2-head filament printer at this time, a single head pellet extruder, and that's the reason why we wanted to start, but we didn't know if it works or not, and that's the reason why we gave this Tukmaker device a chance, and we were really surprised how good it works. What I have to say is really the screw is something which very often changes from company to company. So the screw design, this is typically what I see makes the price differences. Anyhow, I have to say the screw which is inside the Tukmaker does the job quite good at the moment. You cannot use it for mixing, that's true, but for printing it looks pretty good.
And we're actually running out of time, so let's see if we can get 1 or 2 more questions in before we wrap it up. The next question is, what is the minimum diameter of the nozzle that you can use?
Okay, we actually, for our clients, we go from 0.4 millimeters up to 5 different millimeters, up to 5 millimeters diameter. So 0.4 to 5 millimeters. I don't know if Frank has worked with diameters below 0.4.
No, 0.4, we typically use also 0.4.
Mm-hmm.
Okay, and I think this might be the final question. Do feel free to ask questions, to send questions to Tukmaker or to Frank if you have any that were not answered during this webinar. But for the last question, I will just ask, is it possible to print with composite materials in pellet extrusion?
Well, it will depend. It will depend on the chemistry of those composite materials. So if you have those pellets available, you need to take you need to take a look at the chemistry of those materials. There are thousands of different composites. So I'm sorry I cannot go more into details, but it will depend on the materials. But yes, I mean, we have tried with different composite materials.
No, it makes sense. A lot of this will depend on the material used and what you want to use it for as well. Well, it is 5 p.m. now. So as I said, if you would like to ask more questions, do feel free to reach out to Tukmaker especially. And thank you so much, gentlemen, for being here today. It was a pleasure. And thank you all as well for attending. Just a reminder, if you would like to rewatch the webinar, it will be available on YouTube in the coming days. If you want a notification, you can subscribe to our YouTube channel, 3D Natives. And thank you again, and see you at the next webinar.